Hi students, it's your professor Dr. Mink, and welcome to the first lecture for CSC223 Computer Science 2. You should know that this course is often called Data Structures and Algorithms at other colleges and universities. And most likely, when you transfer to one of those institutions, you'll see a name similar to that, or maybe even exactly that. And we're going to do exactly as that name indicates. We're going to study data structures and algorithms in Java. So let's get started. We'll start this lecture with an analysis of algorithms. We'll discuss efficiency goals, the concept of algorithm analysis, big O notation, the concept of asymptotic complexity, comparing various growth functions. When I first got into this industry many years ago, decades ago, the efficiency of an algorithm was important because of the amount of CPU time it used. And at that point in time, processors were limited, relatively speaking, to what we have today. And so, although I was in an environment where we were doing some advanced scientific programming for the aerospace industry, we had limited resources as far as CPU speed and memory capacity. So algorithm efficiency was a real concern back then. Now it's a big concern, but for different reasons. And we'll talk about those later in this lecture. The analysis of algorithms involves categorizing an algorithm in terms of efficiency. So let's take a look at an everyday example. Washing dishes. Not something I do, but I guess people still do wash dishes. Suppose you wash a dish and it takes 30 seconds. And then drying that dish takes an additional 30 seconds. Therefore, N dishes require N minutes to wash and dry. Hold that thought as we move forward. Now, back to the dishwashing analogy. Consider a less efficient approach that requires redrying all previously washed dishes after washing another one. So you'd have N times your 30-second wash time plus the sum from I equals 1 to N of I times 30. So the time for N dishes is 30N plus 30N times N plus 1 over 2, which is actually 15N squared plus 45N seconds for N dishes. When we go to analyze an algorithm, we need to define the size of the problem the algorithm is designed to solve. The dishwashing problem has an N size, N being the number of dishes to be washed and dried. For a search algorithm, the size of the problem is the size of the search pool. For a sorting algorithm, the size of the program is the number of elements to be sorted. We must also decide what constraint we're trying to efficiently optimize. Is it time complexity or CPU time? Or is it space complexity, memory space? Back when I got into this industry, we had both constraints, and you'd be shocked to know how long some processes took because of both memory and time or CPU speed constraints. Now, CPU time is generally the focus. So a growth function shows the relationship between the size of the problem n and the value optimized, which is time. Most often it is time. Here we introduce a key term in this lecture, asymptotic complexity. So the growth function of the second dishwashing algorithm is T sub n, which is 15n squared plus 45n. It's not necessary to know the exact growth function for an algorithm. We are mainly interested in the asymptotic complexity of an algorithm, the general nature of the algorithm as n increases. And you'll see the factor that's most important in calculating the complexity is the highest power of n. So in the dishwashing problem, the term with the highest power was n squared, and that is the dominant term of the growth function, i.e. the term that increases most as n increases. So obviously n squared is going to increase more rapidly than n, and n cubed more than n squared, etc. So in this table you'll see as n increases, 15n squared, the dominant term when analyzing asymptotic complexity, increases much more rapidly than 45n. The coefficients and the lower order terms become much less relevant as n increases. Therefore, we say that the algorithm is order n squared, which is written O of n squared. This is called big O notation. And there are various categories of big O notation. Two algorithms in the same category are typically considered to have the same efficiency. However, that doesn't mean they have equal growth functions or behave exactly the same for all values of n. They're just simply in the same big O category. Here we take a look at some sample growth functions in their big O category. Before we get into this, please know I placed a video on big O notation from an individual I subscribe to on YouTube. It's very good, beginner video. Please watch that, and you'll see in that video many of these growth functions are graphically depicted, and it helps you to understand the time complexity of these growth functions. So T of n equals 17 is O of 1, it's constant. You've got the logarithmic O of log n, O of n log n, O of n squared quadratic, O of n cubed cubic, and O of 2 to the n is exponential. A person might assume that with the advances in the speed of processors, and because of mass production and supply and demand, the ready availability of large amounts of inexpensive computer memory, algorithm analysis would no longer be necessary. However, nothing could be further from the truth. When possible, finding a more efficient algorithm is always a better solution than finding a faster processor. Let's take a closer look. Here we have a table comparing 4 growth functions of algorithms A, B, C, and D. If a system can currently handle a problem of size n in a given time period, what happens to the allowable size of the problem if we increase the speed of the processor by a factor of 10? As shown in this slide, the linear case is relatively simple. Let's take a look at algorithm A with a linear time complexity of n. Its performance is indeed improved by a factor of 10, which means that the algorithm can process 10 times as much data in the same amount of time given a 10-fold speed of the processor. However, let's take a look at algorithm B with a time complexity of n squared. This algorithm is improved, its time complexity is improved by a factor of only 3.16 by increasing the speed of the processor by 10. Why did we not get the full 10-fold increase in the problem size? Because the complexity of algorithm B is n squared. So our effective speed up is only the square root of 10, which is 3.16. Let's take a look at two graphs comparing growth functions. And this one, we have a relatively small input size of n. And you can see already as n increases, the various growth functions diverge dramatically based upon their big O notation. And as the power of n increases, or you introduce logarithmic functions, things change dramatically. Now notice in this graph, as n gets very large, the differences between the growth functions become very obvious and very dramatic, which should tell you why developing an efficient algorithm is of critical importance, especially when you're going to log lots of cycles on that function. For us to determine the order of an algorithm, we have to first determine how often a particular statement or set of statements is executed. Therefore, we have to determine how many times the body of a loop is executed. To analyze loop execution, the first step is to determine the order of the body of the loop. And then we'll multiply the order of the body of the loop by the number of times the loop will execute relative to n. Keep in mind that n always represents the problem size. So n loop executions times O of 1 operations results in an O of n efficiency. Now, let's take a look at another example. If the progression of the loop is logarithmic, as it is in a loop on this slide, then the loop is said to be O of log n. Note that when we use a logarithm in an algorithm complexity, we almost always mean log base 2. Since each time through the loop, the value of count is multiplied by 2, the number of times the loop is executed is log 2n. A more interesting situation occurs when loops are nested. In the case of this nested loop example, we must multiply the complexity of the outer loop by the complexity of the inner loop to find the resulting complexity. So take a look at this nested loop. Both have a complexity, both loops independent of the other have a complexity of O of n. So we would multiply the complexity of the inner loop, n, by the outer loop, and the overall efficiency is O of n squared. So in the previous example, we learned that we find the order of the loop by multiplying the order of the body of the loop by the number of times the loop is executed. But what happens if the loop contains a method call. In this case, we must determine the order of the method before we can determine the order of the entire code segment. Let's suppose that the purpose of the method is simply to print the sum of integers from 1 to n each time it's called. Well, what is the time complexity of this method? Keep in mind that only executable statements contribute to the time complexity. So in this case, all the executables are O of 1, except for the loop. The loop, on the other hand, is O of n. So then we would multiply O of 1 times O of n, and know that the time complexity of this code segment is still only O of n. Now, if we had a much more complex method call that perhaps had a loop within it or had a complexity of higher than O of 1, then we'd not need to multiply that total complexity of the method call and anything happening within it by O of n. I know a lot of this is quite abstract, and we will continue as we move forward with the data structures portion of this course to emphasize big O notation and the role of time complexity of functions. Thanks for watching. Have a great day.